Greetings of the day. I am Dr. Ronika Parmar and I welcome you all in this lecture. Today we are going to discuss an exciting realm of physics, semiconductor physics. Semiconductors are the basic building blocks of modern electronics, and understanding their principle is the key to the technology around us. There are various semiconductors material and we are going to discuss about them today. So, today's outline of the topic is structure of matter, structure of an atom, concept of energy level, atomic structure of semiconductor materials, ionization, energy band theory, energy band diagram, classification of material based on energy gap, that is conductors, insulators, semiconductors. Structure of matter. So, let us begin with the today's topic, that is structure of matter. The matter which occupies the space may be solid, liquid or gas. That is, the substance that fills the space can be of solid type, liquid type or gaseous in nature. According to the modern electron theory, matter is composed of three fundamental particles which are invisible to bare eyes, that is neutrons, protons and electrons. The three fundamental particles are visually invisible particles. We cannot see them with our bare naked eyes. So, they are made of neutrons, protons and electrons. Combining these three makes up a matter. The proton is positively charged and the electron is negatively charged. The neutron is uncharged, that is, it is electrically neutral in nature, possessing no charge. That means the electrons have negative charge while the protons have positive charge. The neutrons has no charge, making this electrically neutral in nature and it remains uncharged. See, there are electrons and there are protons which are equal in number. So, the energy between the two, the positive energy and the negative energy is cancelled out by each other. Thus, they become electrically neutral in nature. Thus, the overall electric charge of the matter is 0 or it is uncharged. The information about these three particles is provided in this table. So, there is a fundamental particle, then the nature of the charge and the mass. Here we can see that, and as I have told you, the neutron is having no charge, it is uncharged, it is neither negative nor positive. The protons are positively charged and the electrons are negatively charged. And here we can see the mass of the neutron and proton is almost equal while the electron is lighter. We can see the mass is 9.107 into 10 to power of minus 31. So, here we can see that the mass of electron is very less in compared to the neutron and proton. Structure of an atom. All the protons and neutrons are bonded together at the center of atom. This is called nucleus, while all the electrons are moving around the nucleus. So, we can say that the nucleus, also known as the center of an atom, is where all the protons and neutrons are bonded together, while the nucleus is surrounded by the electrons. The entire electron population is in motion. In a normal atom, the number of protons is equal to number of electrons. As neutrons are electrically neutral, an atom as a whole is electrically neutral. That is, in a typical atom, there are exactly as many protons as electrons. Since neutrons has no electrical charge, so does the entire atom. Hence, the entire atom is electrically neutral. The number of protons in an atom is called as its atomic number, or we can say that atomic number is the number of, is represented by the number of protons, while the atomic weight is approximately equal to the total number of protons and neutrons in the nucleus of an atom. That is, the term atomic number refers how many protons are present in an atom, while the sum of the protons and the neutrons in an atom's nucleus is roughly represented as atomic weight, or it is also known as atomic mass. The electrons are arranged in different orbit or shells at a fixed distance from the nucleus. Each shell can contain a fixed number of electrons. In general, a shell can contain a maximum number of 2n to the power of 2 electron, where n is the number of shell. That is, the electrons are placed in the variety of orbit or a shell at a predetermined separation from the nucleus. A fixed number of electrons are allowed in each shell. Generally speaking, a shell can hold up to 2 into n to the power of 2 electron, where n represents the number of shell. So, let us discuss about the first shell. So, in the first shell, the first shell occupancy can be maximum of 2 electron. So, how this 2 came? So, number of electrons in the shell is 2 into n to the power of 2. So, for the first shell, 2 into 1, as the shell number is 1. So, 2 into 1 to the power of 2. 1 of the power of 2 is 1 and 2 into 1 is 2. Hence, the maximum number of electron that the first orbit can occupy is 2. Let us see for the second orbit. For the second shell, it can occupy maximum number of 8 electron. How this 8 came? So, number of electrons in a shell is equals to 2 into n to the power of 2, where n is the number of orbit. Here when I say shell or orbit, it means the same. So, 2 into n to the power of 2. So, number of orbit is 2. So, 2 into 2 to the power of 2. So, the total is 8. Hence, in the second shell, maximum occupancy of electron is 8. The electron will have more energy if it is located away from the nucleus, whereas the electron will have less energy if it is located near to the nucleus. So, this means that the energy of an electron depends upon the distance from the nucleus. As I have told you, it rotates along the orbit. So, if an electron is far away from the nucleus, it will have large amount of energy. In comparison to the electron which is near to the nucleus, it will have less amount of energy. Hence, the energy of an electron depends upon the distance from the nucleus. It will be higher if it is further away and it will be lower if it is closer. The outermost shell is called the valence shell, and the electron in this orbit are called valence electrons. Hence, valence electrons are those that are found in the valence band, and it is the outermost orbit of the atom. So, here in this diagram we can see the center part is the nucleus and the electrons are rotating at different orbit, and we can see as the nucleus is positively charged, it will attract electrons toward it. So, the electrons which are near to the nucleus will be attracted more toward the nucleus, and as they move away, they will have high amount of energy with them. So, we can say that the electrons which are near to the nucleus have less energy in comparison to the electrons which are far away from the nucleus will have more energy. Each shell has energy level associated with it. Closer the shell to the nucleus, more tightly it is bounded to the nucleus and possesses lower energy. That is, each shell has a corresponding energy level. The shell is more tightly bounded to the nucleus and has less energy the closer it is to the nucleus as shown in the figure. So, when some additional energy is imparted to the electron move next to the next orbit, which is further from the nucleus, and actually it gets completely removed from the force of attraction of the nucleus. The electrons move to the next orbit, which is away from the nucleus, and it becomes completely free of the nucleus force of attraction when an additional energy is provided to them, and it completely leaves that atom. An electron which is not subjected to the force of attraction of the nucleus is called free electron. Such free electrons are basically responsible to the flow of current. That is, a free electron is one that it is not pulled towards the nucleus by its force of attraction. These unbounded electrons are essential for the flow of current. The flow of current is because of these free electrons. More the number of free electrons, better will be the conductivity in that material. Therefore, the conductivity of metal increases with the number of free electron. More number of free electron, better will be the conductivity of any material. The semiconductor such as germanium and silicon has 4 electrons in their valence shell, that is in their outermost shell. So, 4 electrons are found in these cells or in the outer cells of the semiconductor. So, wherever there are 4 electrons in the outermost shell, these materials come in the category of the semiconductors. So, here we can see that the atomic structure. This is the atomic structure of gallium and this is the atomic structure of silicon. Here we can see that there are various number of cells. Let us talk about silicon. Silicon has 3 orbits and we can say the first orbit has 2 electrons, second orbit has 8 electrons and the third orbit has 4 electrons in the outermost shell. Similarly, we can see the case of germanium. In the outermost shell there are 4 electrons. So, these 4 electrons forms a covalent bond with each other, satisfying to one another. Hence, they form the structure of semiconductor. So, in the semiconductors are those atoms or those materials which has 4 electrons in their outermost shell. When there are 4 electrons in the outermost orbit, the semiconductor material is referred to a pure intrinsic semiconductor. Thus, the term pure or intrinsic semiconductor refers to semiconductor material which has 4 electrons in their outermost orbit. Now, let us discuss about ionization. The process of losing or gaining an electron which converts electrically neutral atom to charged ion is called ionization. This means that ionization is the loss or gain of an electron that changes the electrically neutral atom into a charged ion. If an electron is extracted from the outermost shell of an atom, then the overall negative charge of the atom decreases as it loses negative charge in the form of an electron. That is, the total negative charge of an atom decreases if an electron is removed from its outermost shell, because it loses negative charge in the form of an electron. Some atom as a whole loses its electrical neutral nature and becomes positively charged. Such an atom is called a positive ion. Similarly, by any means, if an electrically neutral atom gains an additional electron and it becomes negatively charged, and it is called negative ion. The valence band electron are shared by forming a bond with the valence electron of an adjacent atom. Such bonds are covalent bond. That is, by joining force with the valence electron of an adjacent atom, a bond is created to share the valence electron. The covalent bonds are these kind of bonds. When such electrons from the covalent bonds, the energy level associated with the valence electron merge into each other. This merging forms an energy band. The valence electron energy level combines with one another when such electron from covalent bonds. An energy band is created by this merger. The energy band formed due to the merging of energy level associated with the valence electron, that is the electrons in the last shell, is called valence band. The energy band formed due to merging of energy level associated with the free electron is called conduction band. Hence, the valence band is the energy band that results from the fusion of energy levels related to the valence electrons or the electron in the last shell or the outermost orbit. Conduction band refers to the energy band that results from the fusion of energy levels linked to the free electrons. The energy gap which is present separating the conduction band and valence band is called forbidden band or forbidden band gap, in which the electron cannot exist. We can say that the forbidden band or the forbidden gap is the energy gap that exists between the conduction band and the valence band and cannot support the existence of electron. The forbidden band, even if I say forbidden band or forbidden gap, this means the same. So, this is the graphical representation of the energy bands in the solid. This is called energy band diagram. Such energy band diagram of solid silicon is shown in this figure. Here we can see in this figure y axis shows energy. So, starting from the lowest one. So, looking at the figure, the y axis shows energy, and as we have discussed, the orbit which is closer to the nucleus will have lowest energy. So, that is represented by the first band. The second band will have energy greater than the first band, but less than the outer orbit. As we have discussed the structure of silicon, which had 3 orbits, first, second and third. The second one had 8 electrons. So, it will have energy greater than the first band, but lower than the third band. Now, we can see the valence band and the conduction band. This forms the outermost shell of the silicon atom, and we can see there is a gap between the conduction band and the valence band. This gap is called the forbidden energy gap, or it is just sometimes said as energy gap. So, in this energy gap, no electron can exist. The electron can never exist in the forbidden gap. Either it will be in valence band or in the conduction band. Hence, whenever we will be discussing the energy band, we won't be discussing about the first band or the second band. We will be always discussing about the valence band and the conduction band only, or the outermost shell only, because the electrons at the outermost shell forms the current, not the first or second band. So, whenever further in the electronic discussion, we will be discussing about the bands, then we will be discussing only about the valence band and conduction band. From the first figure, that is the figure shown here, we can see that the x-axis shows the interatomic distance and the y-axis shows the energy gap, and this diagram shows the 3 energy states into the structure of the silicon. So, N1 represents the first orbit, N2 represents the second orbit, and N3 represents the third orbit. And here we can see that as we move away from the orbit, as we move away from the nucleus, the energy between the N1 is less N2 is between N1 and N3, and N3 has the maximum energy. So, the orbits in an atom are further divided into s,p,d,f orbitals. So, as in this silicon there are sp, so we will be discussing only about sp. So, sp at n is equals to 3, there will be only s and p orbital. So, in the figure you can see the splitting of the energy bands and the formation of the valence band and the conduction band. About the SPDF orbital we will be discussing in the further lectures. The energy associated with the forbidden band is called energy gap and it is denoted as Eg. It is measured in the unit, that is electron volt. The unit of energy is in joules, but the unit of joule is very large to discuss such energies associated with the electrons. Hence, such energies associated with the electrons are measured in electron volts and it is denoted as EV, and the 1 electron volt is equals to 1.6 into 10 to the power of minus 19 joules. So, here let us discuss about the classification of materials based on energy gap. Based on the ability of various materials to conduct current, the materials are classified into conductors, insulators and semiconductor as shown in the figure. So, first figure is for the conductors. Here we can see that the energy gap between the conduction band and valence band does not exist. We can see the conduction band and valence band overlap each other. Either the gap will be very less or they will be overlapping each other. So, in the case of the conductors, there will be no energy gap and the electrons can freely move from the valence band to the conduction band. Now, let us discuss about the insulator. Here we can see that the energy gap between the conduction band and the valence band is too high. It is so large for any electron to move from the valence band to conduction band. It requires a large amount of energy to move any electron from the valence band to the conduction band. So, the transition of electron in these cases are very rare. These act as insulator. They does not allow the current to flow through them. The third figure is for semiconductor. Here you can see there is energy gap in between the conduction band and valence band, but it is less than the insulator and greater than the conductor. Hence, they are called as semiconductors. So, here there will be an energy gap existing and the electrons which are provided with the energy, equivalent energy to move from the valence band to conduction band, they conduct to the valence band to conduction band on gaining a small amount of energy. So, let us discuss about the conductors in detail. It has been mentioned earlier that a material having large number of free electron conducts very easily. In conductors, large number of free electron exist at the room temperature. So, the energy gap does not exist between them. The figure shows the energy band diagram for a conductor. The valence band and the conduction band are overlapping in the conducting material, or in this conductor the valence band and conduction band overlap each other. Hence, the conduction is very easy and a high amount of current flows in these circuits. So, the example for the conductors are copper, aluminium, silver. Generally, metals are known as very good conductor because the energy gap between the conduction band and valence band is almost 0 or they overlap each other. So, here we can see that the possible energy bands for metals. So, if the bands are partially filled or they are overlapping on each other, they allow the flow of electrons. Here we can see the valence band. In the first figure we can see the valence band is full and the conduction band is partially filled, hence the conduction is allowed. Or we can see in the second figure, it is showing overlapping allowed energy bands. So, the conduction band is overlapping with the valence band, hence the transmission of electron is quite easy in this case. The metals have very low resistivity, hence they are good conductor of electricity. So, let us discuss about the insulator. In the insulator, the energy gap is too high. Even at very high temperature or under high voltage, these materials do not conduct. They are very good not conducting materials. For example, diamond. Diamond is an insulator. It has the energy gap of 6 electron volt. Other insulating materials are wood, mica, paper, glass, etc. So, here we can see the energy bands for the insulators. Here we can see that the allowed energy is empty and the allowed energy is completely filled. So, if the allowed energy bands are completely filled, no transition of electron will take place, hence it will act as insulator. Semiconductors are those material which has energy gap around 1 electron volt or more. So, here at normal temperature few free electrons exist, but at absolute zero temperature these are perfect insulators. The energy gap depends upon the temperature in the case of semiconductor. In the case of semiconductor, temperature plays a significant role. The energy gap for silicon is 1.12 electron volts, while for germanium it is 0.78 electron volts. The silicon and germanium are the semiconductor which we normally use. These semiconductors are highly dependent on the temperature. As the temperature changes, the nature of the material or the characteristics of the material changes in the case of semiconductor. So, here we can see that the allowed energy state is partially filled. When it is the case of partially filled, there is easy transaction of electron from one state to another state. Hence, the current flows whenever we have a closed loop circuit. Now, the next topic is direct band gap and indirect band gap. The maximum conduction band energy and the maximum valence band energy occurs at the same K value. Then these are the direct band gap materials. A semiconductor with this property is said to be a direct band gap semiconductor. The transition between the two allowed bands can take place with no change in the crystal momentum. Here we can see that the minima of the conduction band and the maxima of the valence band lies on each other, as we can see in the figure. The direct nature has a significant effect in the optical property of the material, and gallium arsenide is an example for it. It is used in laser and optical devices. The difference between the minimum conduction band energy and the maximum of the valence band energy is still defined as the energy gap or EG. A semiconductor whose maximum valence band energy and the minimum conduction band energy do not occur at the same K value is called as indirect band gap materials. Silicon, germanium are the example of this semiconductor, and most of the semiconductor applications happen because of this indirect band gap semiconductors. Thank you for your patience listening.